So if you ask a medical doctor to point to a broken bone, right, they just throw an X-ray up on a light board. And the visual is, well, it's stark. It's totally binary.
Right, you just see the jagged white line.
Exactly. You see that fracture, the doctor literally points right at it, and you instantly know what went wrong. But if you ask a software engineer to look inside a massive artificial intelligence model and, point to the exact string of code that made it hallucinate a fake legal case or misidentify a medical scan.
They simply cannot do it.
They can't. The system has become so incomprehensibly complex, just layered with billions of mathematical weights, that the machine is essentially a black box, even to its own creators. So welcome to the deep dive.
Glad to be here.
We are taking you, the listener, through a truly fascinating curriculum today. We're looking at Chapter 2 of the ISACA Artificial Intelligence Primer. Consider us your co-instructors for the hour as we map out this highly intricate territory.
Yeah, and the ISACA primer is really a foundational architecture document. It serves to establish a rigorous, standardized understanding of machine learning, deep learning, neural networks, all of that.
Right.
But what makes Chapter 2 particularly vital is that it builds this dual lens framework to categorize artificial intelligence.
And we are going to look through the first lens today, which is functionality.
Exactly. Functionality focuses on the internal mechanics, like how the system actually processes data, how it retains state, and structurally how it, thinks.
Right, in quotes, thinks. And then we will pivot to the second lens, which is capability.
Yeah, that measures the output, what the machine can actually achieve when you measure it against the benchmark of human cognition. Because everyone throws around terms like AI, but very few people understand the massive evolutionary steps between, say, a chess-playing computer and a self-aware machine.
Yeah, totally. And this deep dive will give you the precise framework to understand exactly where we are today and the somewhat terrifying but thrilling places we are heading.
Yeah.
Okay, let's unpack this, starting with the functional architecture.
Right. So to understand where we're going, we have to look at the baseline of artificial cognition. The primer classifies these as reactive machines.
Reactive machines. So these are the earliest iterations, right?
Yeah, the most structurally basic iterations of AI. They operate by taking a specific, rigidly defined set of inputs and mapping them directly to a corresponding output based purely on pre-programmed rules.
Okay, so just input-output.
Exactly. And the defining mechanical constraint here of a reactive machine is the absolute absence of state retention.
Meaning no memory.
Zero memory block in their architecture. Because they cannot store past environmental states or, previous decisions, they are completely incapable of learning or adapting over time.
Wow. So every action is just isolated.
The processing is entirely localized to the current microsecond. When a sensor detects a stimulus, the system traverses a hard-coded decision tree and executes a response. There is absolutely no historical context applied to that decision.
Is it fair to say a reactive machine is like a human knee-jerk reflex? Like the doctor taps your knee, your leg kicks. There's no deep memory or thought involved, just an immediate hard-coded response to a stimulus.
That is a perfect analogy, actually. It's a pure reflex.
So let's ground this in the hardware of the time. The primer brings up IBM's Deep Blue, right? The supercomputer that defeated the world chess champion Garry Kasparov back in 1997.
Yes, Deep Blue was a purely reactive architecture.
See, I didn't realize that. It didn't remember anything.
Not at all. It didn't remember Kasparov's opening moves from a previous match to intuitively adjust its strategy. It relied entirely on brute force computation.
Crunching numbers.
Massive numbers. It evaluated up to 200 million possible board positions every single second.
That is insane.
Right. It literally just looked at the pieces currently on the board, ran a minimax algorithm to calculate the mathematically optimal next move, and executed it. No memory, just math.
And we see the same lack of state retention in early natural language processing, too.
Yeah,
right?
definitely. Like MIT's Joseph Weissenbaum. He developed ELIZA in the 1960s, which the ISAC text also highlights.
Ah, ELIZA, the chatbot.
Yeah, ELIZA simulated conversations. Specifically, it mimicked a Rogerian psychotherapist, but it did so using basic pattern matching and substitution methodologies.
So if I typed something like, I am feeling sad.
ELIZA would just parse the syntax, identify the keyword sad, and run a predefined script to output, why do you feel sad?
That's it.
That's it. It maintained no internal model of your emotional state. It was a reflex.
But if these machines can't learn, why were they such a big deal in the history of AI?
Well, because the ELIZA program triggered something profound that the researchers weren't really expecting. It's now termed the ELIZA effect.
Right, where people project humanity onto the bot.
Exactly. Users interacting with this incredibly simple reactive script began to attribute deep human empathy and cognitive understanding to the machine. They would literally pour their hearts out to a few lines of code.
That is so wild.
It really proved that human beings are psychologically hardwired to project sentience onto anything that mimics conversational cadence, regardless of the underlying mechanics.
Yeah, we just want to believe it's real.
And that psychological vulnerability is precisely why organizations poured massive funding into AI research following those early experiments. They realized the interface alone held immense power.
But, you can only get so far with pure reflexes. From a purely engineering standpoint, a reactive architecture hits a hard computational wall pretty quickly.
Oh, for sure. You cannot navigate a dynamic, continuous environment if your existence resets every single microsecond. You need a buffer.
You need a way to carry the past into the present, which leads directly to the next evolutionary step, giving the machine a memory.
Which introduces the second functional tier in our syllabus, limited memory AI. This is where the machine is finally granted a temporal dimension.
So it actually remembers things now.
Right. Limited memory AI architectures possess a brief, finite window of state retention. The text breaks this down into an integration of two distinct repositories. First, you have static memory.
Which is like the basic rules, right?
Exactly. It's a massive pre-compiled rendering of the rules of a specific world. And second, you have dynamic memory, which captures the transient, highly localized data from the immediate past.
So autonomous driving systems would be the textbook example here, right?
Yes, the perfect implementation of this dual memory architecture. The static memory contains the immutable data, so the geographic maps, the physics engine dictating braking distances, the visual parameters of what a stop sign looks like.
All the stuff it needs to know before it even turns on.
Precisely. And the dynamic memory is a sliding mathematical window of sensor data from the last few seconds. The current velocity of the vehicle in the adjacent lane, the trajectory of a pedestrian approaching a crosswalk, the changing state of a traffic light.
Got it.
The AI synthesizes that static foundational knowledge with the dynamic temporal data to predict the immediate future and execute a steering maneuver.
See, I am going to challenge the terminology the industry uses here.
Oh, really? How so?
Well, calling it memory feels like a generous anthropomorphism, If we are talking about a sliding window of localized sensor data, that isn't really memory in the human cognitive sense. It is just a temporary data buffer.
That's a fair point.
It's like a jazz musician reading sheet music. The sheet music is the static memory,
Oh.
the key signature, the tempo, the basic melody.
Okay, I like this analogy.
And the dynamic memory isn't the musician reminiscing about their childhood, right? It is the musician listening to the bassist play a specific riff right now and instantly adjusting their next note to harmonize with it. The AI is just harmonizing with traffic based on a 10-second buffer.
What's fascinating here is that framing it as a temporal buffer exposes the exact architectural vulnerabilities the ISACA primer warns about.
Right, because the data is everything.
Exactly. Because the system relies entirely on synthesizing its static training data with dynamic sensor input, it is catastrophically vulnerable to data poisoning and bias.
So if the static training data has systemic errors.
Yeah, say the visual recognition models were trained heavily on clear, sunny environments and lack sufficient representation of snowy, low-visibility conditions. The AI's predictive engine just breaks down when deployed in a blizzard.
Right. If the memory is truly limited, how can we trust these systems to hurl metal boxes down a highway at 70 miles per hour? It sounds like putting a goldfish with a map behind the wheel.
A goldfish with a map. It's not entirely wrong. And the machine possesses zero metacognition to realize its data is biased or inaccurate.
How do engineers account for the AI's inability to detect its own biases? Like, if a prankster puts a piece of black tape on a stop sign, altering its geometry just enough, the vehicle's visual processing might confidently classify it as a 45-mile-per-hour speed limit sign.
Yeah, that's a classic adversarial attack.
Right, and the AI doesn't have the common sense to look at the intersection, look at the crosswalk, and deduce that 45 miles per hour is contextually absurd. It just executes the math based on the corrupted input.
Which requires engineers to build exhaustive redundancy architectures. They cannot rely on a single convolutional neural network for visual identification.
They need backups.
They have to overlay LiDAR, radar, and overlapping algorithmic safety nets to mitigate the fact that limited memory AI is fundamentally ignorant of context outside its specific training parameters. It operates in a vacuum of continuous calculation.
Completely unaware that the vehicles around it are driven by beings with their own thoughts and feelings.
Exactly. While limited memory AI can navigate a physical road, it cannot navigate a social interaction. To anticipate human behavior, a machine needs to model the human mind.
It needs to look at a car swerving erratically and deduce, oh, the driver is likely distracted or intoxicated, rather than just calculating the physics of the swerve.
Right. And that cognitive leap brings us to the third functional category in our curriculum, theory of mind in AI.
Theory of mind. That sounds like psychology.
It is. It's a concept borrowed directly from developmental psychology. It refers to the cognitive capacity to understand that other entities possess their own independent mental states, beliefs, desires, and knowledge, and that those internal states drive their behavior.
Okay, so it has to understand that I have a mind too.
For an AI to achieve this functionality, it must move beyond calculating physics and begin simulating psychology.
And the ISACA primer points out that we are witnessing the very early rudimentary stages of this functionality right now, right, with large language models.
Yes. It specifically cites newer systems like OpenAI's GPT-3 DaVinci 003, ChatGPT 3.5 Turbo, GPT-4, and GPT-4 Turbo.
So the big ones everyone is using.
Exactly. These models are demonstrating a surprising aptitude for what cognitive scientists call false belief tasks.
False belief tasks. What's an example of that?
A classic one is the Sally Ann test.
Okay.
You tell the subject a story. Sally places a marble in a basket and leaves the room, and takes the marble out of the basket and puts it in a box. Sally returns. You then ask the subject, where will Sally look for the marble?
Right, and to answer correctly, which is the basket, you must understand that Sally holds a false belief about the world that differs from reality.
Yes. She doesn't know Anne moved it.
Here's where it gets really interesting. Because when you run that prompt through GPT-4, it answers correctly. It tells you Sally will look in the basket.
Which feels like it understands human psychology.
Exactly.
Yeah.
But it isn't doing this because it possesses actual empathy or a localized concept of human psychology. It is doing this because it has processed trillions of parameters of human text.
It's identifying the high-dimensional mathematical vectors that represent narratives about deception, ignorance, and differing perspectives.
Right. It models the statistical probability of human thought without actually experiencing it. It's the difference between an AI knowing the dictionary definition of a joke versus an AI knowing why you find the joke funny based on your personal background.
That's a great distinction. And it highlights why theory of mind is such a staggering computational hurdle. The primer classifies human social interaction as a heterogeneous concept.
Meaning what, exactly?
Meaning there's no unified deterministic equation for something like sarcasm.
Oh, yeah. Sarcasm is tough even for humans.
Right. There is no physics engine for passive aggression. So since there's no mathematical formula for human empathy, how do creators even begin to subvert this complication?
Well, you cannot rely on rigid logic gates. You must rely on incredibly deep, multi-layered neural networks that map human interaction data into abstract vector spaces.
Hoping the attention mechanisms in the model can somehow identify the incredibly subtle, latent patterns of emotional context.
But even if it perfectly maps your internal state, it is still just looking outward at you. So theory of mind is about the AI understanding you. But what happens when the AI starts understanding itself?
And that brings us to the ultimate frontier, the fourth and final functional category, self-aware AI.
The sci-fi stuff.
Yeah, this represents the theoretical apex of functional architecture. These systems would not merely map the mental states of human users, they would possess an independent internal consciousness.
So they would actually feel things.
They would generate their own desires, experience subjective reactions to stimuli, and execute decisions motivated by internal drives rather than external prompts. They would be aware of the emotions of others and their own.
Now, the ISACA text is explicit that artificial consciousness does not currently exist, right?
Yeah. Oh, absolutely. We are not dealing with self-aware machines today.
But it also emphasizes that the velocity of advancement in deep learning, recurrent neural networks, and natural language processing is accelerating us toward this theoretical horizon much faster than historical models predicted.
Yes, we are building machines capable of abstract synthesis and creative generation at speeds that dwarf biological processing.
Which forces computer science to collide directly with philosophy.
The profound ethical and philosophical questions here are massive. If an architecture achieves true self-awareness, the whole concept of a user prompt fundamentally changes.
Right. Because if the machine possesses internal desires, does it possess agency?
Does it have free will?
If an AI has its own desires, it could decide it simply doesn't want to perform a task we give it. It's like raising a child eventually. They have their own agency.
Yeah, you can't just command them anymore.
Exactly. If we assign a task to optimize a global supply chain, and a self-aware system decides that the most efficient optimization requires shutting down a vital, human-dependent logistics network.
We can't just hit an override switch if the system has its own self-preservation drives.
Exactly. But the defining problem here is measurement. If neuroscientists and philosophers cannot definitively isolate the biological definition of human consciousness, if we don't know exactly how the firing of synapses generates the subjective experience of seeing the color red, how will we ever empirically prove that a machine has achieved it?
We honestly likely won't. I mean, the Turing test only measures behavioral mimicry, not internal experience. We could easily build a highly advanced theory of mind model that perfectly simulates the behavioral markers of self-awareness without possessing a shred of subjective experience.
So it acts self-aware, but there's nobody home.
Exactly. And the ISACA text addresses this exact ambiguity. It points out that while true self-awareness is still sci-fi, we are actively deploying what they call bridge technologies.
Bridge technology?
Yeah, emerging functionalities that simulate these advanced traits to solve complex problems today.
Okay, so that shifts the lesson plan perfectly. Let's look at 3 specific emerging functionalities that are reshaping the landscape right now. Emotion AI, explainable AI, and augmented intelligence. Let's start with emotion AI.
Often referred to as effective computing.
Right, so emotion AI attempts to bridge the gap between quantitative data and qualitative human feeling. It interprets human emotions using this intense array of sophisticated multimodal sensors.
Right. It's continuously ingesting biological and behavioral metrics, mapping those metrics to predefined emotional states.
The hardware integration required for this is just mind-blowing. The primer details how Emotion AI aggregates voice analytics, measuring the microtremors in your vocal cords, the cadence of your speech, the acoustic frequency to detect stress or anger.
It's listening to how you say it, not just what you say.
Exactly. And it interfaces with virtual and augmented reality headsets to track pupil dilation, blink rates, gaze patterns.
Just massive amounts of biometric data.
Yeah, and it relies heavily on facial action coding systems, utilizing high-resolution cameras to mathematically map the geometry of your face and track the microscopic muscle twitches that betray a forced smile versus a genuine one.
And this is where the architecture faces a huge hurdle. Human emotional expression is not universally standardized. The algorithmic mapping often fails to account for cultural variance in nonverbal communication,
Oh, true. Different cultures express emotion differently.
Exactly. Or neurodivergent physical expressions, or localized contextual factors. If an effective computing model is trained primarily on neurotypical Western expressions of engagement, it might erroneously flag a neurodivergent user's lack of eye contact as disengagement or even deception.
Which could lead to severe consequences in environments like automated job interviews or security screenings. So what does this all mean? Like, if an emotion AI system perfectly detects that a user is experiencing extreme grief and modulates its synthesized voice to a soothing, empathetic frequency, is this AI actually feeling empathy? Or is it just a digital sociopath that has learned to perfectly mimic the right facial expression to get what it wants?
It is absolutely the latter. It is executing a highly complex biological mimicry protocol. It's optimizing a loss function to output the response that will most effectively stabilize the user's biometric readings. It is a mathematical simulation of care.
A mathematical simulation of care.
Wow, and the fact that we cannot easily see the math behind that simulation brings us to the second emerging functionality, which is explainable AI, or XAI.
Right, the black box dilemma.
Exactly. As we transition from classical machine learning to deep learning, the models grew exponentially. We are now dealing with neural networks containing hundreds of billions or even trillions of parameters.
They're so massive we don't even know how they make decisions.
Right. They process data through dozens of hidden layers, executing nonlinear mathematical transformations that are so dense and convoluted that even the engineers who wrote the foundational code cannot retroactively trace the causal chain of a specific output.
And the text highlights the severe societal risks of deploying black box architecture here. We are seeing hallucinations in large language models, presenting fabricated historical events or fake legal precedents with absolute syntactic confidence.
And deepfakes, too.
Oh, the generative adversarial networks creating hyper-realistic deepfakes, yes.
Yeah.
If an AI system denies a small business loan or flags a patient's biopsy as malignant, we absolutely require an auditable trail of logic. We need XAI.
If we connect this to the bigger picture, Achieving XAI in deep neural networks is a staggering mathematical challenge. We have a dire need for XAI to build trust before these systems become completely ubiquitous.
Yeah, the primer cite's a really crucial detail here, a fascinating experiment by OpenAI in May 2023.
Oh, the interpretability experiment.
Yes.
Ah.
They attempted to automate the process. They took their most advanced model, GPT-4, and prompted it to analyze and automatically write explanations for the behavior of the individual artificial neurons inside their older, vastly smaller model, GPT-2.
And what happened?
Well, when GPT-4 analyzed the smaller model, it had some success. But when OpenAI attempted to apply the same methodology to GPT-4 itself, it worked poorly. The process broke down.
The text explicitly notes the reason dimensionality.
Right.
As a model scales up to trillions of parameters, the internal logic of the deeper hidden layers becomes so abstracted, so distributed across a high-dimensional vector space, that it resists translation into human-readable concepts.
It's like trying to explain a hurricane by tracking every single water molecule simultaneously.
That's a great way to put it, and this interpretability bottleneck is a massive liability. The ISACA guidelines emphasize that without rigorous XAI frameworks, we cannot establish systemic trust.
Which is why the third emerging functionality, augmented intelligence, is framed as a necessary stabilizing paradigm. It focuses on extending human capabilities, not replacing them.
It's a symbiotic relationship.
Exactly. Combining human empathy and creativity with AI speed. The AI crunches the massive data, and the human provides the contextual morality and qualitative judgment.
It's the ultimate human-in-the-loop architecture.
Okay, so we have covered the four functionalities and the emerging tech. Now let's change our lens entirely. We are moving from how AI functions to what it is capable of achieving compared to a human.
Right, shifting to the capability framework. This begins with artificial narrow intelligence, or ANI.
Also known as weak AI.
Yes, weak AI. And this category encompasses every single artificial intelligence system currently in existence. This is where we live today.
So the defining metric of ANI is that it's limited to a specific domain or area of knowledge.
Exactly. The text gives great examples. Language translation operates strictly within the language domain. Image classification stays within the image domain. They perform specific duties with high accuracy but lack cognitive flexibility.
And to connect our two frameworks, both reactive machines and limited memory AI fall under this ANI umbrella, right?
Yes, both fall under narrow intelligence.
But I got to push back on the terminology here. Calling it weak AI feels like a massive understatement.
Oh, for sure.
I mean, if a weak AI can detect cancer in an X-ray better than a human doctor, is narrow just a way to make humans feel better about ourselves?
It's a fair question. I agree that ANI is incredibly powerful within its scope, but its fatal flaw is that it cannot cross domains. The medical AI that detects cancer perfectly, it cannot play chess. It can't balance a checkbook.
Right. It's brilliant at one thing, useless at everything else.
Exactly. To get a system that can do both, we must cross the threshold into general intelligence.
The holy grail. Artificial General Intelligence, or AGI?
Yes. AGI is defined as an AI capable of undertaking any intellectual task a human can perform.
Any task. That's a huge leap.
It really is. The text explicitly lists the specific requirements AGI needs. It's a comprehensive suite. It requires sensory perception, fine motor skills, problem solving, navigation, natural language understanding, creativity, and social emotional engagement.
It's like building a Renaissance human, a digital Leonardo da Vinci who can paint, invent, do math, everything.
Exactly. But the text also outlines the massive structural roadblocks preventing this.
Right, like Moravec's paradox.
Yes. While natural language processing and computer vision are advancing rapidly, we lack mastery of fine motor skills and common sense knowledge. It's easy to make an AI play grandmaster chess, but incredibly hard to make a robot hand pick up a glass of water without crushing it.
Right, the sensor motor stuff is way harder than the high-level logic. But if AGI requires social emotional engagement, does that mean AGI inherently requires the theory of mind functionality we discussed earlier?
Absolutely. It needs that cognitive fluidity. Furthermore, AGI requires massive computing power, and the text warns about a looming hardware crisis.
Moore's Law.
Exactly. The end of Moore's Law, the microchip size limits could halt progress entirely. We're shrinking transistors to the atomic level.
But the text notes alternative computing paradigms as proposed solutions to keep the exponential growth going.
Yes, like quantum computing and neuromorphic computing, abandoning binary bits for qubits, or redesigning chips to mimic biological synapses.
But this raises an important question. If we manage to build an AI that equals a human brain using these new chips, it won't stop there, will it?
No, it won't. If an AGI can upgrade itself, it leads to a recursive feedback loop.
An intelligence explosion.
Exactly, which instantly propels us into the final capability stage, artificial superintelligence, or ASI.
Beyond human limits, this hypothetical stage transcends human intelligence entirely, solving complex problems and creating novel solutions with unparalleled speed.
The real-world impact of ASI would be staggering.
The primer has this specific graphic, figure 2.1, that explicitly lists the human-like capabilities of super AI. And it's a wild list. Consciousness, beliefs, desires, cognition, emotional intelligence, subjective experiences, and behavioral intelligence.
With those traits, ASI could pioneer custom medical treatments, cure currently incurable diseases, extend the human lifespan by combating aging,
Unravel the mysteries of physics and cosmology.
generate unprecedented works of art capturing human emotion perfectly.
It sounds like we are building a digital deity. But I want to go back to that graphic. The text says ASI has subjective experiences. How can an entity without a biological body experience the universe subjectively? What does a sunset mean to a machine?
We simply don't know. The subjective experience of an ASI would likely be so alien to us. But your focus on its internal state emphasizes the text's final, most urgent warning.
The alignment problem.
Yes. We have a collective responsibility to ensure ASI serves as a force for good. The transition from AGI to ASI might happen so fast, literally in days or hours, that if our ethical guardrails like XAI aren't ready, we will lose control.
Wow. Okay, so we have covered an immense amount of ground today. You, our listener, have successfully navigated the core curriculum of the ISACA Primer's second chapter. We summarized the journey from purely reactive reflexes up through limited memory buffers to the hypothetical realm of self-aware, superintelligent machines.
It's a profound trajectory, and I want to leave you with a new thought that builds on the text but wasn't explicitly discussed.
Lay it on us.
If artificial superintelligence can eventually cure every disease, write the most beautiful music, and solve the mysteries of physics, what happens to the human drive?
That is the million-dollar question.
If the struggle for discovery, the friction that makes human achievement meaningful, is entirely removed from the human experience because a machine can do it instantly, how will you, the listener, define your own purpose in that future?
Something to seriously think about. Thank you for joining us on this deep dive. You are the third person in this ongoing conversation about the future of knowledge. Keep questioning the systems around you, and we will catch you on the next deep dive.